Hey everyone, welcome back. So we're now on to chapter 4, and this chapter is one of the most theoretical chapters in the book because we introduce this concept of a vector space. And so again, we're only going to do problems in this video series. I'm not going to talk about like how to theoretically think if something's a vector space or not. I'm just going to teach you guys the mechanics here. Okay? And so the problem we're going to look at today, or in this video, comes from a quiz that it gave out last semester, and is essentially to determine why each of the following sets are not vector spaces. Okay, and so if you do not know what a vector space is definitionally, have the book definition open in front of you. If you don't know what it is conceptually, it's okay. It takes a while. We'll cover it in recitation. Your TA will cover recitation. Your lecturer should cover it, and yeah, so just know that a vector space for now is just a set of something, okay, of vectors, but anything can be a vector. So the only thing you really should think about is that vectors don't necessarily need to be like something that has direction and magnitude. A vector could be like a matrix entry or a solution to a differential equation, which happens to be then the first problem that we're going to talk about. So problem 2 here talks about, or on the quiz this is problem 2, but each of the following fails to be a vector space. Okay, for each set, describe which properties of vector spaces they fail to satisfy. All right, and so this first set then, set A, is going to be the solutions to the differential equation y double prime plus y is equal to 1. Okay, and so why is this not a vector space? Why are the solutions of this differential equation not a vector space? Well, say that I have two solutions. Say that I have two solutions. Let's call them y1 and y2. All right. Then we want to check if this is closed under addition, right? That's a property of a vector space. So then y1 plus y2 has to be a solution. All right. And so if I plug in, then y is equal to y1 plus y2. So I make this substitution, and now I have y1 plus y2 double prime, okay, plus y1 plus y2. All right, this needs to equal 1, all right, because the solutions to this differential equation, if it's a vector space, then they're closed under addition. So y1 plus y2 needs to be a solution. However, what do we see, right? We see that this becomes then y1 double prime plus y2 double prime plus y1 plus y2, and that's because the derivative, all right, is linear, and so when you take two derivatives, you can just distribute the double prime in. But this is equal to y1 double prime plus y1 plus y2 double prime plus y2. Okay. Well, what's the problem here? Well, y1 is a solution to this differential equation up here, right? y1 is a solution to y double prime plus y equal to 1. So that means y1 double prime plus y1 is equal to 1. And y2 is also a solution to this differential equation. And so that means y2 double prime plus y2 is also equal to 1. And so then we get 1 plus 1 is equal to 2, which means that y1 plus y2 is not a solution to this differential equation. And so this is not equal to 1, so it's not a vector space. Or it's not closed under addition. All right. So not closed under addition is why it's not a vector space. Another perfectly acceptable answer is that there's no zero vector, right? So if y were equal to 0, I would get 0 plus 0 is equal to 1. Well, that's not true, and so there's no 0 in this vector space, and therefore that's another perfectly acceptable reason for why the solutions to this differential equation don't form a vector space. All right, what's the next problem? So there's 3 parts to this problem. Part B then is the set of positive integers. All right, so why aren't the set of positive integers a vector space? Well, here's the thing. Maybe I should clarify this a little more. This needs to say real vector space right here. Okay, so why isn't the set of positive vectors? Why isn't the set of positive integers a real vector space? Well, a real vector space means that the scalars, where I do scalar multiplication, are real numbers. So, for instance, let the scalar k equal, I don't know, square root of 3. Okay? Well, what's square root of 3? It's an irrational number, right? And so, if I take any integer, let's say 37. Okay, so this is just an example. It's any random integer, right? Any random positive integer. I take 37, then under scalar multiplication, I have 37k, which is, in this case, 37 root 3 if k equals root 3. But what's the problem there? 37 root 3, this is not an integer, right? That's an irrational number because root 3 is an irrational number, and we have an integer times a rational number. It's irrational. So 37 root 3 is not an integer, and so under a real vector space, the set of over the field of real numbers is how it's technically supposed to be said, but the set of positive integers is not a real vector space because I can choose any scalar that isn't an integer, right? And then all of a sudden, under scalar multiplication, the resulting number may not be an integer. And so it's not closed under scalar multiplication. All right. The last problem. This one's a bit hard. So the set is a set of tuples a comma b in R2, which means this it just means that a is a real number and b is a real number. R2, you can also think of it as like the xy plane, such that vector addition is defined as AB plus CD is equal to ACBD. So this is kind of mind-bending here, but essentially we're not saying, I'm defining addition differently, okay? Because all addition has to be in a vector space is that it has to be some kind of operator, all right? It doesn't strictly have to be addition is equal to A plus C is equal to A plus C, right? I can say A plus C is defined as multiplying A and C together. So keep that in mind. Addition is defined this way, kind of weird, but scalar multiplication is defined normally. So k times AB is equal to KA, KB, for K being a real number. Okay? All right, so what's wrong here? This one's actually pretty tricky because if we actually check addition, all right, if it's closed under addition, it is closed under addition because so let's think of it this way, right? For something to be closed under addition, all that means is that the resulting tuple has to be an R2, right? And so if I have A1B1 plus A2B2, well, this is just equal to A1A2 comma B1B2, like I have it defined by the addition operation. But the thing is, these guys, A1B1, they're all real numbers. A2B2, they're all real numbers. And so the multiplication of A1A2 and B1B2, they're also real. And so this tuple then is an R2, right? And so it's closed under addition. Furthermore, it's closed under scalar multiplication, which is obvious because I'm taking K, which is a real number, I'm multiplying by A and B, all right? So it's closed under scalar multiplication. So these arguments that I used in part A and part B don't apply to part C. What else? Well, the zero vector also exists, right? 0, comma 0. So it's closed under scalar mult. The zero vector exists because 0, 0 is an R2, right? A and B just have to be 0. So what fails? Well, what else is there about a vector space? Well, it needs to be commutative, right? That means AB plus CD needs to equal CD plus AB, right? Well, AB plus CD is equal to, right, AC BD, but this is equal to CA DB, which is CD plus AB, right? Based on how we defined addition. And so that works. Guess what? Associativity also works. That also holds. So what do we have left, right? What do we have left? Well, there's 10 properties, and the zero vector exists, your identity exists, right? What's the identity? What's the additive identity? This one's kind of trippy. Well, A1B1 plus A2B2 is equal to A1B1. Well, that means that A2 is equal to 1 and B2 is equal to 1. Since, remember, when you add, you just multiply the terms, right, in the correct position of the tuple, and so the additive identity is actually 1, 1, right? All right, this is getting kind of trippy. What else? Inverses. Inverses also exist because what is an inverse? Well, most people think that an inverse means that you get to 0. That's not true. An additive inverse just means that A1B1 plus A1B1 inverse is equal to the additive identity. Usually the additive identity is going to be 0, right? Because when we think about adding real numbers, right, 2 plus 0 is 2. So the additive identity is 0. And so to find the inverse then, it would just be negative 2, right? Because 2 minus 2 is 0, and 0 was our additive identity. So the inverse gets us to our additive identity, okay? in this case, A1 B1 inverse is equal to 1 over A1 comma 1 over B1. And these two entries are all real numbers because you can take fractions, right? As long as A1 B1 is not 0, but that actually is a problem. And so that if A1 B1 are 0, there actually is no additive inverse, right? And that's a big problem. So the additive inverse doesn't exist for 0, 0, which means it's not a vector space, right? Because think about it, 0, 0, how do we get to the additive identity, which is 1, 1, right? My additive identity is 1, 1. How do I get to this additive identity from 0, 0 when under addition, right? Remember, addition is defined in this wonky way right here. I can't ever get to 1, 1 because 0 times anything is going to be 0, right? So the additive inverse doesn't exist for every element in my vector space. So it doesn't exist for 0, 0, okay? And so this is one way to show that it's not a vector space. Another way to show that vector space, it actually fails distributivity. And so if you try to distribute a scalar, right? So let's do k times v plus w, all right, where let v equal v1, v2, and w equal w1, w2, all right? So v and w are our tuples, and k is a scalar, right? And so this is distributing the scalar over addition. You can distribute the addition of scalars over a vector, and you can also distribute a scalar over vector addition. This is the latter. We're distributing the scalar k over vector addition right here, right? So you can check either one. Well, you have to check both, but it fails for both. We're only going to check one of them. This becomes k, right, v1 v2 plus w1 w2, right, which is k times v1 plus w1 comma, or sorry, not v1 plus w1 because addition's defined weird, v1 w1 comma v2 w2, which is k v1 w1 comma k v2 w2, right? But this is not equal to kv plus kw, because what's kv plus kw? Well, kv plus kw is equal to k v1 v2 plus k w1 w2. So this is then kv1 comma kv2 plus kw1 plus kw2, and you see where this is going, or kv1 comma kw2, right? And because of our wonky plus sign, right, because of our wonky addition function, this then becomes k squared v1 w1 comma k squared v2 w2, right? Yeah, these guys are not equal. So it fails distributivity. It fails the additive inverse because 0, 0 doesn't have an additive inverse. And yeah, so that's why this guy is actually not a vector space. And so this is a lot of work. These are 3 problems. You should go through them. A and B are kind of easy. C is like, you don't really see these on on exams. Well, you do, but you do for subspaces more than vector spaces. And we'll talk about subspaces in the next videos coming up. I think I have one more vector space video that I want to do, but yeah, I would look through then this problem and understand why these sets are not vector spaces and how I can verify that these sets are not vector spaces. All right, great.